So, good morning, students. I welcome you all for another lecture on the course Digital Circuits. In this class, I'm going to explain about a concept called asynchronous counters. In the last class, we discussed about synchronous counters. We know that the counters are used to count the input clock pulses. Coming to asynchronous counters. Asynchronous counters are also called ripple counters. The another name of asynchronous counters is ripple counters. The reason for this is the clock pulse is directly applied to only the least significant flip-flop present in the counter. For a higher order flip-flops, the clock pulse is either uncomplement Q or complement, that is a Q bar outputs of the lower order flip-flops. That means in these asynchronous counters, the clock pulse we are not applying simultaneously to all the flip-flops present in the counter. Only from the clock source, the clock pulse is applied to only the least significant flip-flop. For higher order flip-flops, we are applying the clock pulse from the previous stage flip-flop. That is, the previous stage outputs either Q or Q bar is act as clock pulse for the next immediate higher order flip-flop. Asynchronous counters are only designed for fixed counting sequence. But in case of synchronous counters, we can design it for any counting sequence. But it is not possible for the case of asynchronous counters. Always the counting sequence should be fixed, that is 0, 1, 2, 3, 4, like that. The counter is designed for both the counting as well as down counting style, like a synchronous counter. These asynchronous counters are designed by using purely JK flip-flops or T flip-flops. Because in this asynchronous counters, the flip-flop should be operates in toggle state. The toggle state condition we will get only from JK flip-flop or a T flip-flop. But in case of synchronous counters, we design it with the help of any type of counter. There is no this type of a restriction. There we calculate the flip-flop inputs, but here we are not calculating any flip-flop inputs. Always the flip-flop inputs are connected to logic 1. The count value of the counter is called mod value of the counter. We know this. The mod value of the counter is less than or equal to 2 power n, where n is equal to number of flip-flops present in the counter. If the mod value is less than 2 power n, we know that such counters we are calling as truncated counters. This point also already I mentioned in the synchronous counters also. And in this case also, you may have a truncated asynchronous counters. And another one is normal counters, asynchronous counters. For them, the total count value is 2 power n. The counting style of asynchronous counter is out and out is depends on the triggering method what we are using for the flip-flops, along with the output, that is either Q or Q bar of a previous flip-flop is connected to the next flip-flop as a clock pulse. Based on this, the counting style of the counter was defined. That I was mentioned in this following table. The triggering notations, we know that there are two triggering notations. One is a positive triggering and second one is a negative triggering. If I use the positive triggering, along with I was connected uncomplemented output of a previous flip-flop as a clock pulse to the next flip-flop, such counter counting style is down counting style. The triggering method is same, that is a positive triggering, but instead of connecting uncomplemented output, if you connect a complement output, the counting style of a counter is up counting. If a triggering notation is a negative triggering and we connect uncomplemented output as a clock pulse to the next stage, the counting style is up counting. Triggering notation was same, again negative triggering. Instead of that, here we are connecting complements. Sorry, here friends, here it is a complementing output Q prime or Q bar is a connected as clock pulse to the next stage, then it is act as a down counter. That means the counting style of counter is down counting. For example, if I go and design a 4-bit asynchronous counter, we know that the 4-bit asynchronous counter is designed with 4 flip-flops. I'm already told you the asynchronous counters are either designed by using JK flip-flops or T flip-flop. Either you use JK flip-flop or T flip-flop, the flip-flop should always connected to logic 1. So that's why here for these 4 flip-flops, I was connecting T input to logic 1. And I've already told you that in this asynchronous counter, the clock pulse is not applied simultaneous to all the flip-flops. From the clock source, the clock is only applied to the least significant flip-flop. For higher order flip-flops, we are applying clock pulse from the previous stage, either Q output or Q bar output. Here, these flip-flops are used positive edge triggering. We know that this arrowhead indicates edge triggering notation. And here there is no bubble in front of this arrowhead, so that here these flip-flops are operates at positive edge triggering. If it is a positive triggering and the complement output of a previous flip-flop is act as a clock pulse, according to our previous table, the counting style of a counter is nothing but up counting. See here, friends, the clock pulse is only applied to the least significant, and this flip-flop Q bar output is act as clock pulse for the next higher order flip-flop. Similarly, its complement output is act as the clock pulse for the next higher order flip-flop, and so on. It is a 4-bit asynchronous up counter because here I was used 4 flip-flops. Initially, I was assuming that all my flip-flops are clear. That means Q0, Q1, Q2, Q3. So this is a least significant flip-flop, so that your counting sequence is Q3, Q2, Q1, Q0. This is an order you should follow to take a count value. So Q3, Q2, Q1, Q0. Initial all are zeros. If I apply first clock pulse here, then this flip-flop should be toggle. That means the output should be interchange. The output of Q0 previously is 0, so it toggles. That means the value is changes to 1. Here that is 1, automatically Q bar value is 0. That 0 is applied here. That 0 can't drive this flip-flop 1 because here we are using positive triggering, so that here we are always expecting logic 1. But here unfortunately we are getting 0, so that this flip-flop is can't turn on. If it is not turned on, automatically is also not turned on. So they are maintaining the previous values, that is 0, 0, 0. But the Q0 value becomes 1. So that is your first stage, that is 0001. If I go and apply my second clock pulse, again this flip-flop was toggled. Previously its value was 1, now it is changes to 0. And automatically Q bar value is 1. Then this flip-flop drive now. And previously its value is 0. Now this flip-flop was toggled, then its value changes to 1. And then once Q value is 1, Q bar value is 0. That 0 can't drive this flip-flop 2 as well as flip-flop 3. So that these values are maintained previous values, that is 0, 0. And for this applying a second clock pulse, Q3 value 0, Q2 value 0, but Q1 value is 1, Q0 value is again 0. That should be the count value. If I apply third clock pulse, again your flip-flop was toggled. Previously Q0 value is 0. So then it toggles its value changing from 0 to 1. That 1, here Q0 bar value becomes 0, so that it can't drive this flip-flop. So that this flip-flop value, previous value, it maintains. And automatically these flip-flops also not active, so that previously here I have a 1 and here 0 and here 0. The state of my counter is 0, 0, 1, 1. So that should be state of your counter after applying of third clock pulse. If I go and apply fourth clock pulse, the output of this flip-flop toggles because this flip-flop is a drive with this clock pulse. Previous value of Q0 is 1, so it toggles, its value becomes 0. Then automatically Q0 bar value is 1, then it drives this second flip-flop. Again, T input is 1, so that the output should be toggle. Previous Q1 value is 1, so it toggles, it becomes 0. Then automatically Q1 bar value is 1, then it drives flip-flop 2, so that the output of this flip-flop 2 was toggle because T input is 1. Previously Q2 value is 0, and now it toggles, it becomes 1. It is 1, Q2 bar value 0, then again this flip-flop can't drive. Then the state of your counter is 0, 1, 0, 0. That is your cases. Like that, by applying of all these 15 clock pulse, if you are applying 15th clock pulse, all these flip-flop values becomes 1, 1, 1. If I go and apply 16th clock pulse, friends, this flip-flop was toggled. That means previous its value is 1, now it becomes 0. That 0, then Q naught bar becomes 1, it drives this flip-flop. So T1 value is 1, so that this flip-flop again toggles. Previous its value is 1, so it becomes 0. Again, Q1 bar becomes 1, and it will drive flip-flop 3. And the flip-flop for 3 Q2 value becomes 1, so that it toggles. Q2 value previously 1, so it will become 0. Again, Q2 bar value 1, then it drives last flip-flop. And it toggles because T3 input is equal to 1. Previous Q3 value is 1. Then it toggles, it becomes value 0. That means the state of your counter applying a 16th clock pulse is 0, 0, 0, 0. That means what are the state we identify once at the beginning of this counter, that is all 0 state, that state again repeats. Then the number of clock pulses its count is from 1 to 16. Again, we are getting the initial state. So this is a counting sequence for this asynchronous up counter, which can be designed by using 4 flip-flops. This a 4-bit asynchronous counter we can also call mod 16 counter, because the number of counts we are getting from this operation of counter is 16. And similarly, if I go and design asynchronous down counter with a 4-bit, only the change what I have to do is, previously I was connecting Q naught bar as a clock pulse to higher order stages like this for up counting style. Now I would like to design a asynchronous counter with a down counting style, so that instead of Q bar connection, I'll go with Q naught connection. The rest of the connection is as it is. Initially, I was assuming that by using this asynchronous input, I made this flip-flop output becomes 1. That is here 1, here 1, here 1, here 1. Preset. It is an asynchronous input. We know that irrespective of clock pulse, this asynchronous input will make the output of flip-flop is equal to 1. Here 1, here 1, here 1, here 1. That's why at a 0th clock pulse, my state of counter is 4 1s. Now, if I apply first clock pulse here, that is applied to the least significant, and T0 input is 1, so the output should be toggle. So previously it is 1, now it becomes 0. That 0 counter drive this flip-flop, so that these flip-flops are maintained in the previous stage, so that the state of counter is 1, 1, 1, and its value is 0. Is this? If I go and apply second clock pulse, again T0 value is 1, so your flip-flop should be toggled. Previous its value is 0, now it will becomes 1. That 1 drives this second flip-flop, and it will toggles because T1 input is 1. Previous Q1 value is 1, now it will becomes 0. That 0 can't drive flip-flop 2, so that it will maintain previous value, and T3 is also not a drive, so that T3 also maintain previous value. So the state of your counter is 1, 1, 0, 1. That is this. Like this, the counting style is in down counting style. If you're coming to the last case, that is if you're applying a 15th clock pulse, then what happens is all your flip-flops should maintain all 0 space. If all flip-flop values are all zeros, then if I go and apply the 16th clock pulse, then what happens is this flip-flop was toggle, previous its value 0, now it will becomes 1. Then that 1 drives this second flip-flop, and second flip-flop also toggle because T input is 1, previous Q1 value is 0, so it will becomes 1. That 1 drives this flip-flop also, again this flip-flop also toggle because T input is equal to 1. Previous Q2 value is 0, now it will becomes 1. That 1 drives the last flip-flop, and last flip-flop also toggle because T input is equal to 1. That means Q3 value previously 0, now it will becomes 1. Then the state of your counter is 1, 1, 1, 1. So again, I was getting this particular condition. So that the number of clock pulses counted by this counter is again 16. So it is called a mod 16 counter also. But here the counting style was down counting. So I already told you that for up counting, so positive triggering, Q bar should be connect. For down counting, for positive triggering, we should go and connect uncomplement output of flip-flop as a clock pulse to the next higher order stages. For these are two cases, that is for this 4-bit asynchronous down counter and previously designed 4-bit asynchronous up counter, the total number of counts counted by the counter is equal to 16. In these both the cases, the number of flip-flops present in the counter is equal to 4. The number of counts we are getting is 2 power 4, that is equal to 16. I'm already told you that the number of counts counted by the counter is less than or equal to 2 power n. Here it is equal to 2 power n case condition was satisfies. Next, if I shift it to the count value is not equal to 2 power n. So the best example is asynchronous decade counter, that is mod 10 counter. So mod 10 counter here I was using again a up counting style. Sorry friends, here it is Q bar here. Q bar is connected to your flip-flops clock pulse, right? So positive edge triggering and Q bars are connected to here, then automatically your counting style is up counting style. This counter counts only from all zeros to 1001 because these are the 10 different counts that should be counted by your decade counter. Decade counter is mod 10 counter, the count starting from 0 to 9. What happens if the counting is 1010? So 10 in the sense most significant bit is 1, that is Q3 is 1, Q2 0, Q1 is 1, and Q0 also 0. Here Q3 and Q1 both are given to the input of NAND gate. For a NAND gate, both inputs are 1, output should be 0. That 0 is given to the inputs of all your flip-flops present in the asynchronous counter to the clear input or a reset input. This reset input is again an asynchronous input, irrespective of the clock pulse. This clear input or reset input makes the output of the flip-flop is equal to 0. That means whenever if I was getting a counting value of 1010, that is 10, then automatically your counter should be cleared. That means the counter state goes to 4 zeros. That means this counter is only counting from 4 zeros to 1001. There are total 10 counts. So that it is called asynchronous counter or a decade counter or a mod 10 asynchronous counter. So this is one of the truncated counter example. I hope you understand the asynchronous counter, both the truncated counter case as well as non-truncated counter case. Now I would like to see the comparison between synchronous counters and asynchronous counters. So synchronous counter and asynchronous counter. We know that asynchronous counter we can also call a ripple counter. So the first point is in synchronous counter, all flip-flops are triggered with the same clock pulse simultaneously applied. We know that. In synchronous counter, what are the flip-flops we have in a counter? All they are getting clock pulse from common source. That means all flip-flops are active simultaneously. But coming to asynchronous case, it is not the same. The clock pulses we are only applied to the first flip-flop. That means all the flip-flops may not be triggered or activated simultaneously. Coming to the second point, once the flip-flops present in the counter was triggered simultaneously by taking same clock, then the counter speed is faster. So asynchronous counter is faster than synchronous counter speed is faster than asynchronous counter. The reason is here all the flip-flops present in the synchronous counter get a clock pulse from same source. But coming to asynchronous counter, the speed is lower than synchronous. Why? Because here all the flip-flops present in the counter may not be active or triggered simultaneously. And next, third one is synchronous counter is also called parallel counter because all the flip-flops got a clock pulse parallelly and all flip-flops are activated simultaneously. But coming to asynchronous counter, it is not parallel counter, it is a serial counter because at any instant of time, if you observe that asynchronous counter operation, only one flip-flop in the counter should be active. And next one is synchronous counter designing is complex. Why? Because we know that we are following some fixed procedure while designing of synchronous counters. Start from designing of a state diagram and we complete such designing of logic diagram by using logic gates along with the flip-flop. So that the designing of synchronous counter is a little bit complex. But coming to asynchronous counter, the designing is easy because we need not be calculated any the flip-flop input functions. We are not designing any state table. We are not designing any state diagram. We are not designing any excitation table. We are not doing any simplification. Simply the flip-flops what we have in asynchronous counter, they should be operates in toggle state. For that, always the flip-flop inputs are connected to logic 1. And one more thing is, this asynchronous counters we designed purely by using ZK and T flip-flop, because in those two flip-flops only we are getting toggling condition, so that the designing is easy in case of asynchronous counter. And last one is synchronous counter will operate in any desired count sequence. We know that we can design synchronous counter for any counting sequence, but it is not possible in case of asynchronous. Asynchronous counters were always designed by using a fixed counting sequence. We were unable to design a synchronous counter what are the counting sequence we have. So that is the comparison between synchronous counters and asynchronous counters. I hope you understand what asynchronous counters are, in that how it is designed, both the truncated counter as well as non-truncated counter. And then we are observing the comparison between synchronous counter and asynchronous counter. So thank you for patient listening. In the next class, we'll go and discuss some other topic. Thank you once again.